If we're going to talk about the history of robotics, first we need to talk about what a robot actually is. And for such a common term, it's surprisingly slippery to define. But technically speaking, a robot is just a machine designed to accomplish a task. That's it. Now, it might sound like that would cover everything from a 4-function calculator to NASA's Pleiades supercomputer, but that is not what we're talking about here. When we talk about robots, we're really talking about machines that use their programming to make decisions. For example, if you, a human, decide to pick up a coin from the ground, there are 3 main steps you have to go through. First, your eyes need to see the coin, and then send that information to your brain. Then, your brain processes that input and uses things like previous experience to make a decision to pick it up. Eventually, your brain sends messages to your body to grasp the coin. Robots go through a similar process, but without getting the Slim Jim at the gas station. They can go through that process because most of the time they have the components that let them carry out each step. They have sensors for input, control systems for decision-making, and end effectors for output. Sounds simple enough, but developing each of these components can be challenging. Sensors have to be able to detect things like images and sound accurately. Effectors have to be flexible and fast enough to do what we need them to do. And the control system has to make all of the decisions necessary to get the sensors and effectors working together. Of course, there are so many different kinds of robots that these components can vary considerably, but that's the basics of robot anatomy. Now, if we tried to talk about every advance that's been made in every subfield of robotics in just the past half-century, we'd be here all day. But to understand how we've gotten this far and why robots haven't taken over the world yet, we first have to talk about how the development of industrial, humanoid, and military robots got the field where it is today. Industry is a good place to start because that's where robots first became useful. Since factory work can be repetitive and often involves lifting lots of heavy stuff, it's perfect fit for a machine. The world's first ever industrial robot, Unimate, was installed on a General Motors production line in New Jersey in 1961. Weighing in at nearly a metric ton, it was basically a giant robot arm. Its instructions, programmed on a huge magnetic drum, told the arm to stack and weld hot pieces of metal over and over again. Soon, other car companies got in on the game, installing their own robotic arms, but this first generation of robots was still in its awkward stage. The arms weren't particularly flexible, they were often powered by clunky hydraulics, and they were ultimately difficult to program. So when a robotic arm called IRB-6 came along in 1974, it was a pretty big deal. This was the first electric industrial robot that was controlled by a microcomputer. It had 16 kilobytes of RAM, it was programmable, and it could display 4 whole digits with its LEDs. Developed by Swedish engineering firm ABB, this robot was used to perform inauspicious tasks like polishing steel tubes, but it was a crucial step toward developing robots that were easier to program. But while controlling robotic arms was getting simpler, another issue came up. You can give a robot as much programming as you want, but if it can't see, it's not going to be able to do even seemingly simple things like figure out which box should go where on a pallet. Crude visual scanners had been around since the 50s. They could only see black and white, and the resolution was worse than what you get from a flip phone camera. But to give vision to industrial robots, engineers had to tap into another field that would completely change the robotics game: artificial intelligence. Now, artificial intelligence, or AI, is another broad, vague term used to describe any attempt to make a computer do something that we'd normally associate with human intelligence, like translate languages, or play chess, or recognize objects. In the 60s, the problem was that even though AIs were getting better at complex reasoning tasks, like playing chess and proving mathematical theorems, it was incredibly difficult to actually get the programs to interact with the real world. There's a difference, for example, between figuring out the ideal placement of a wooden block in a theoretical model and actually moving those blocks into place. Because moving them involves a whole series of discrete decisions and actions, and the robots of the time simply couldn't manage that. For robots, vision isn't just about taking pictures, it's also about recognizing objects so that they can react to things in situations in real time. By the late 1970s, engineers had developed new algorithms that allowed cameras to recognize edges and shapes by using visual cues like highlights and shadows, but these programs were still just experimental, stuck in research labs. That all changed in 1981 when the first industrial robot got the gift of vision. A General Motors factory was once again the guinea pig, implementing a system called ConSight, in which 3 separate robots could use visual sensors to pick out and sort 6 different kinds of auto parts as 1,400 parts per hour moved by on a conveyor belt. Progress! For the next 2 decades, technology kept improving. Industrial robots were able to see better, move faster, carry heavier loads, and handle more decisions. These days, industrial robots robots are advanced enough that it's totally normal for a factory to install a robotic assembly line that handles nearly all of its production. And some industrial robots are heading in the direction of a more general-purpose use, like Baxter, the humanoid industrial robot. Humanoid? Yet again, a very subjective term, but it just means human-like. For robots, that usually implies that they're designed to look and act as human-like as possible. So Baxter, for instance, is nearly 2 meters tall, weighs 136 kilograms, and has a screen for a face. It also has a vaguely human-shaped torso and 2 arms. But more importantly, it can be quickly programmed to do practically anything. If a factory worker or researcher has a task to do, Baxter can probably handle it as long as it's lifting less than 2.2 kilograms because its arms are not industrial strength. But it does need to be told what to do. If you want Baxter to stack some products in a box, for instance, you've got to program it by manually making it do what you want the first time, and then it'll imitate that task. And its shape may be loosely based on a human, but Baxter cannot walk, or climb stairs, or talk. So getting a robot to act like a human has proved to be a whole other ballgame, and it's one that researchers have been working on for decades, and it's been slow going. The Wabot 1 is usually considered to be the first full-scale humanoid robot. Developed by researchers at Waseda University in Japan in 1973, it had arms, legs, and a vision system. It could walk, it could pick things up with its hands, it could even talk. Except that it could only reply with pre-recorded responses to very specific statements, and it took 45 seconds to take one step. This bot and its successor Wabot 2 were a really big deal in their day, but they also pointed out an important fact. It's just much easier to design robots to do one task at a time. So recently the thinking has been, if general-purpose humanoid robotics are out of our grasp, we might as well focus on making something that can do at least one useful task. That's why in the past 10 years there have been more household robots in use than ever, programmed to perform a single function, like vacuuming the floor, mowing the lawn, washing windows, or cleaning the pool. They're not quite rosy from the Jetsons, but they were all made possible by the advances that came before them, like having the ability to sense their surroundings and make decisions in order to navigate the world. And it's not like researchers have given up on the humanoid front. There are humanoid robots in development that can perform some impressive feats. Honda's Asimo, for example, can walk at speeds of almost 6 kilometers an hour, climb up and down stairs, carry a tray, push a cart, among other things. So again, progress. You just can't buy one. For the time being, Asimo is basically a research tool and a spokesmodel for what the future of robotics might look like. But probably the most cutting-edge research going on in robotics today is being done by the military. Take Bear, a military robot that's been in development since 2005. Unlike with humanoid or even single-task robots, in the military, robot design is more about function than form. So Bear has some humanoid components like a head and 2 arms, but instead of walking like a human, its legs are covered in treads like a tank. The legs have a joint that acts kind of like a knee that can rotate all the way around. Using their special limb design, Bear has proven really good at moving through rough terrain, including stairs. It can climb through debris and carry an injured soldier back to base. It can carry light loads, tell it to go to a location, and it'll go there. That's a lot more than most civilian robots can do. But discussion of military robots would not be complete without talking about DARPA. A division of the US Department of Defense, DARPA has been working for the last 50 years to turn even the wackiest of concepts into working technology, and it's been one of the most active promoters in the field of robotics. DARPA has stoked innovation by holding robot competitions. It held contests for autonomous vehicles where robotic cars compete in a race hundreds of kilometers through the Mojave Desert. And in the summer of 2015, 11 teams will compete in the DARPA Robotics Challenge Finals, where human-supervised robots will try to carry out complicated and kind of dangerous tasks associated with disaster response, like scrambling over debris and carrying things to safety. The aim is to develop robots that can be sent into dicey situations without putting human lives at risk, and we're getting there. So robot tech has come a long way since that first robotic arm in 1961. It's just that, as often is the case when it comes to humans and technology, we can dream up awesome designs and uses for robots faster than we can actually invent them. For now, I'm perfectly happy to have a clean kitchen floor and my freedom from the tungsten mines while science takes robotics to the next level.